Hello. So let's continue from where we had left off in the last class. Here we were talking about the Navier-Stokes equations. We talked about the different terms in there. You can see that there was a transient term, there's a convection term, there's a pressure gradient term, there's a viscous term, and then there is a body force term. Okay, that is in the momentum equation. Then you also have the continuity equation, which after the incompressible assumption, you get del dot u is equal to 0, as in the divergence of the velocity vector is equal to 0. So let's go into a little bit more detail into the Navier-Stokes equations. So these equations are nonlinear and difficult to solve. What makes it nonlinear? The nonlinearity is the complicated part in the Navier-Stokes equations. It is what makes it difficult to solve by hand. It is what makes it not amenable to analytical solutions, except under certain conditions, and I'll describe that. So the nonlinear term is the convection term, u dot del u. This is the nonlinear term. This term brings the complexity to the equation. If not for this term, you could actually get an analytical solution for the Navier-Stokes, for the momentum equation. Okay? So if I go to this slide, and if I want to solve the Navier-Stokes equations exactly, if I want to have analytical solutions for Navier-Stokes equations, I have to make certain assumptions. For example, there are certain very specific problems with assumptions where you can actually get analytical solutions for Navier-Stokes equations. So if I have flow between two parallel plates, laminar flow between two parallel plates, where both the plates are stationary. Okay, this is an example where both the plates are stationary. I have laminar flow between these two plates. The nonlinear term can be neglected in this case. If you actually go through the derivation, the nonlinear term can be neglected, in which case you will just have the pressure gradient and the viscous term, and you can solve for it. You can get an analytical solution for this problem. Even if the top plate was moving, okay? So if you have something like this where the top plate is actually moving at a certain velocity, which we call co-ed flow. In this case too, you can actually get an analytical solution. So these are certain specific cases where you can get the analytical solution, but otherwise the Navier-Stokes equations are not amenable to analytical solutions, especially because of the nonlinear term. You can make certain assumptions where you neglect the nonlinear term in certain cases, especially laminar flows, and in those cases you can get the analytical solution. So that is what makes the Navier-Stokes equations complicated, right? Because in the nonlinear term, you cannot get it by hand. So it's not like you can get a solution for the turbulent flows by hand. An analytical solution for the turbulent flow is impossible to get. Now, because of this reason, we have made very little progress with turbulence, relatively speaking, okay? Because we are not able to get analytical solution. And as a consequence, early descriptions of turbulence were mainly based on experimental observations. Obviously now, with the advent of computers in the last 20 to 30 years, we have made a lot more progress. But still, our understanding of turbulence is still limited. Reynolds was the first person to systematically study a turbulent flow, especially the transition from laminar to turbulent flow, through a set of very carefully done experiments. So what he had was a pipe flow filled with water, and I'll show you what the picture looks like. So these are pictures from his paper. These are pictures from his paper, and you will see him standing near his experimental setup. He put down his observations. Remember, this was 1883. There are no cameras to visualize the image. He put down his observations. He drew a cartoonic figure of what his observations were. And that is what is shown here on the right. You have flow in a pipe of possibly water, and then there is a dye streak that is injected into this pipe flow in order to visualize the flow. The colored dye helps you to visualize the flow. And what happened is, as he increased the velocity of the water in the pipe, he started to notice some difference in flow patterns through the visualization of the flow of dye streak. So if I go back, he identified a single parameter that could determine the characteristic of the flow. That parameter is now named after him, and it is called the Reynolds number. That Reynolds number, marked as Re, is given by rho UL over mu. Rho being the density, U being the velocity, the characteristic velocity scale, L being the characteristic length scale, and mu is the absolute viscosity. So if I think about this ratio here, Reynolds number, I have the numerator and the denominator. The numerator represents the inertia forces, and the denominator represents viscous forces. So Reynolds number is the ratio of inertia over viscous forces. As the inertia forces dominate, or as the viscous effects are negligible, Reynolds number keeps increasing, and vice versa. As the viscous forces dominate and the inertia forces are less, then the Reynolds number is very small. This helped him determine the characteristic of the flow, whether it is laminar or turbulent. So as the Reynolds number increases, the viscous effects are negligible. Inertial effects are higher. The Reynolds number increases, the flow tends to be more turbulent. As the Reynolds number decreases, the viscous effects are more dominant, inertia effects are lower, and the Reynolds number is very small, and the flow tends to be laminar. So he came up with this parameter after doing this set of experiments which I have shown here. So here is what happened. He had this flow through the pipe, initially at a certain flow rate of water. He noticed that the dye streak was just flowing through the pipe undisturbed. What do I mean by that? The edges of the dye streak are definite, right? The edges can be well defined. You can see here the edges can be well defined. So you would think that the flow is smooth, and that is why the dye streak is flowing undisturbed, in the sense that it is actually not mixing with the flow. The dye streak remains as a dye streak through the length of the pipe. So this makes us think that the flow might be laminar. Now, when he increased the flow rate of water, he started to notice some differences, okay, where he saw that the dye streak was starting to exhibit some fluctuations in the flow, and that fluctuations is what he has drawn here. Now, as it starts to exhibit some fluctuations, it is starting to mix with the water. There is a little bit more mixing that is happening, that is visible in the flow. So this is sort of transitional, and I'll explain more about this. As he increased the flow rate even more, then the dye streak looked like it completely mixed with the flow. It exhibited some fluctuations, and eventually the dye streak just completely mixed with the flow. You will see some fluctuations here, and then here it is completely mixed. So this tells me that this flow is turbulent. This flow is turbulent. So you can now see the difference between laminar, transitional, and turbulent flow through a set of pictures here, how the flow changes from laminar to turbulent. And all he did was he increased the flow rate. He kept everything the same. The water is the same, the dye streak is the same, the diameter of the pipe is the same. Since the water is the same, since the fluid is the same, the density is the same, and the viscosity is the same in all these three pictures. The only thing that is changing is the velocity. And if Reynolds number is rho u L over mu, and if only velocity is being increased, as in flow rate is being increased, so velocity is being increased, then as you're going from top to bottom, Reynolds number is increased. So as the Reynolds number increases, the flow tends to be turbulent. Flow was laminar, then it became transitional, and then it went to turbulent. For pipe flow, typically the flow is laminar if Reynolds number is less than 2300. This is a laminar flow where the Reynolds number is less than 2300. Experimental observations have shown that to us. If the Reynolds number is between, again, approximately 10,000 and greater than 2300, it is transitional. And if the Reynolds number is greater than 10,000, it is definitely turbulent. So Reynolds number is a single non-dimensional parameter that bulks up all these different properties: the density, the velocity, the characteristic length scale, and the viscosity scale, the viscosity. It bulks all of this up into one single parameter. So no matter what the fluid is, what diameter pipe you have, what velocity you have, as long as that single non-dimensional parameter goes above these numbers that I have written here for pipe flow, you have a certain characteristic of the flow. As in, if it is less than 2300, it is laminar. If it is between 2300 and 10,000, it is transitional. And if it is greater than 10,000, it is turbulent. So that is what it characterizes, right? It characterizes the kind of flow that you can have. Laminar flow, where the edges are smooth, there is not much mixing. And when I say mixing, I am talking about mixing of the dye streak with water. As we saw in the Navier-Stokes equations, if I go back, as we saw in the Navier-Stokes equations, there is a viscous diffusion term on the right-hand side of the momentum equation. And in the viscous diffusion term, there is a viscosity there. It's kinematic viscosity, but that's just absolute viscosity divided by rho, right? Nu, kinematic viscosity, is absolute viscosity divided by rho. So that diffusion term always exists in the sense, since viscosity is a molecular property, molecular diffusion always exists. What changes as I keep increasing the Reynolds number is the convective term gets more and more strong. So the turbulence gets to be stronger, and the macroscopic transport, the enhanced diffusion as we'll call it, the convective transport mixes it faster. I talked earlier about, trying to mix coffee with milk. If you stir it very slowly, you will definitely mix the milk and the coffee, but it will take a while because diffusion is playing a role. Viscous diffusion is playing a role there. Now, if you try to stir it vigorously, you will mix the coffee and the milk faster. That's because convective transport is playing a bigger role there in mixing the coffee and the milk. Hence, it will be a faster mixing. compared to molecular mixing. So that is what is happening here. In the first picture where you have laminar flow, viscous diffusion does play an effect. But the viscous diffusion is not strong enough to make us visualize the mixing of the dye streak and the water. On the other hand, if I keep increasing the Reynolds number, I am tending towards turbulent flow. Then the convective transport is taking over. Then mixing is becoming, convective mixing, the mixing due to convective transport is becoming more dominant. And that is what is causing the mixing of the dye streak. So as you can see in the turbulent picture here, it is completely mixed towards the end. That's because convective transport has dominated viscous diffusion. And that is determined by the Reynolds number. So again, relating this to the Reynolds number, I have inertia over viscous. As the numerator is the inertial term, it is related to the convective transport. The denominator is the viscous term. It is related to the viscous diffusion. As Reynolds number is higher, the convective transport is higher. And I get to mix much faster when the Reynolds number is higher. When the Reynolds number is lower, the viscous term is more dominant, viscous diffusion is more dominant, and so the dye streak stays almost unmixed, or at least to the eye, it seems like it is almost unmixed. So that's what we are trying to summarize in this slide, where two things, right? One is a very enhanced mixing in turbulent flow. That was clear. As you went from laminar to transitional to turbulent, your mixing started to be more vigorous, just like you're stirring it with a spoon. Your mixing is starting to be more vigorous. So here, this is one of the most important features in turbulent flow. The fact that you can achieve enhanced mixing with a turbulent flow. And this is why we want combustion to be turbulent in an aircraft engine. You want it to generate as much power as possible, so that you want the reactants and the oxidizer to mix as fast as possible, so that it can generate as much power as possible in a very short amount of time. So you want the combustion to be turbulent. Or just in a simple case, simply mixing two fluids using stirring. You want it to mix as fast as possible in order to be more efficient. So turbulent mixing is what you're after. Laminar mixing will mix it, but at a very slow rate. Second point, eventually both the mixings are leading to the same outcome. Okay, you achieve the same result, except now with turbulent flow, you are achieving it at a much faster time scale. So that is why we refer to turbulence as enhanced diffusion. I was saying that earlier. It is called enhanced diffusion. You have viscous diffusion or molecular diffusion. Now you have enhanced diffusion because of the convective transport. Going back to the equations again, just to make my point, this convection term that I have shown here, the convection term, the convective transport, is what is responsible for that enhanced diffusion. And the viscous term here is responsible for molecular diffusion, which always exists. Laminar flow and turbulent flow has viscous diffusion, except in turbulent flow, the viscous diffusion tends to be negligible compared to the convective transport. Okay, so a case in point, just to describe all of this, the enhanced diffusion part. So when you're traveling by plane, sometimes the pilot announces, we are going to be hitting turbulence, so just fasten your seat belts. And what does he mean by that? You're going to experience some kind of disturbance. So in order to not hurt yourself, the pilot is actually encouraging you to, it requires you to put your seatbelt on. Okay, so there is a sudden agitation sometimes, especially a few minutes after the flight takes off. And that is because you are leaving a mostly calm troposphere and entering into a planetary boundary layer. That is represented by this picture shown here. Now this is actually from a numerical simulation of atmospheric boundary layer over few kilometers of altitude. So the scale here, the vertical length scale here is a few kilometers. And you will see that this is a vertical cross section showing the turbulent boundary layer filled with chaotic motions. It's clear that it's filled with chaotic motions and many different length scales. We've been now seeing these different length scales. We saw it with the jet in the beginning. So you saw these large scales and small scales. You see the same thing here, except these are now on a much larger scale. It's not like a laboratory jet, it's the atmospheric boundary layer. So the vertical scale here is a few kilometers. The color indicates the magnitude of the variation of the density field. So the density changes with the altitude, right? And that is what the color is indicating here. Increasing from black to yellow to red. And the simulation was performed at Supercomputer. So this is a very high fidelity simulation. But the reason I'm showing this is to actually indicate how that disturbance occurs as you go from one layer to the other. And that disturbance was responsible for the dye streak mixing as you increase the Reynolds number. As Reynolds increased the flow rate, he noticed that disturbance in the flow which led to the mixing of the dye streak. That disturbance is what you're seeing in the atmospheric boundary layer. So that is what you experience, or that is what the pilot calls as turbulence, and which it is, right? It is turbulence due to the planetary boundary layer, which is represented through this picture from a numerical simulation. So that turbulence occurs because the convective transport tends to dominate over the diffusion, tends to dominate over viscous diffusion. So essentially what Reynolds number is it is a balance between inertia and viscous. We knew that from the ratio. Reynolds number is inertia over viscous. So it is clearly a balance between inertia and viscous forces. As one dominates over the other, your flow characteristics change. As inertia dominates over viscous diffusion, flow tends to be turbulent. As viscous diffusion dominates over inertia, the flow tends to be laminar. So that is what we have to try and recognize. Like I was saying earlier, the final result of turbulent mixing due to convective transport, the enhanced diffusion part, okay, the turbulent mixing is the same as that of diffusive mixing. The final result is the same. The final outcome is the same. The mechanisms are different. The physical mechanisms are different. One is obviously mathematically you can clearly see what the difference is. Diffusive mixing is nu del squared u, right, where u is a vector. Turbulent mixing is u dot del u. Mathematically, they are such different terms. One is a non-linear first derivative, where a first derivative term is involved, and the other one is a linear second derivative term. Okay, so both are two different terms mathematically, which means their physical mechanisms are different. So the second point was what I was saying earlier in this slide. The turbulence arises when molecular diffusion effects are quite small compared to the turbulent mixing. So we can call it turbulent mixing due to convective transport, enhanced diffusion, molecular diffusion, or diffusive mixing. So that second term on the LHS of the Navier-Stokes equations, right, that corresponds to macroscopic transport. This is the convective or advective term. The second term on the LHS of the Navier-Stokes equations. That is this one, the convection term. And the second term on the RHS represents molecular diffusion. So this is nu del squared u. And this is the second term is u dot del u. Sorry. U dot del u. So it is clear that both the terms are very different, and also if you look at the viscous diffusion term, viscosity is a coefficient there, right? So viscosity is playing a part, clearly. Viscosity is playing a part. So that should be clear now. So if nu is small, kinematic viscosity or absolute viscosity, again, in this class, mostly we are dealing with incompressible flows. So for us, rho is a constant. For most part of the class, unless we are discussing very specific circumstances, we are discussing cases only where the flow is incompressible. So density is a constant. So for us, absolute viscosity and kinematic viscosity kind of have the same effect. So if nu or mu is small, we should expect the advective nonlinear behavior to be dominant, as in the convective derivative, the convective transport to be dominant compared to the diffusion, which is what you see in a turbulent flow. In contrast to this, if nu is large, then molecular diffusion will be dominant in comparison to the convective transport, and the flow will be laminar. And that is actually the only scenario with certain assumptions where you can get analytical solutions. Analytical solutions are just not possible in turbulent flow, whereas in laminar flow, for very specific cases with specific assumptions, you can get analytical solutions. So that's where we started this from. This part of the lecture, we started by talking about how analytical solutions are possible in laminar flow and how they are not possible in turbulent flow due to certain cases, and specifically due to the nonlinear term. That nonlinear term is what is responsible for the turbulence. Its domination over the diffusion is what leads to turbulence. So here is another snapshot from a numerical simulation, from a simulation done on a supercomputer for an exhaust jet. And the scales is clear, but we have already seen that the wide range of length scales, we have already seen that. But what is also interesting is how vigorously it mixes, right? This jet, you can see how vigorously it mixes, and that enhanced mixing is one of the most important attributes of turbulence. That enhanced mixing is what makes it necessary to have turbulent flows in a lot of engineering applications. That enhanced mixing is due to the fact that your convective transport is dominant over the viscous diffusion. Your turbulent mixing is dominant over laminar mixing, the viscous diffusion. So I hope that is clear. And we have now covered the Navier-Stokes equations in detail, talking about each term and which term leads to turbulent flow. The dominance of which term leads to turbulent flow. I hope now that is clear to you. Thank you.